All right. So today is going to be our last topic in the second module. That means we're going to close down the module number 2, which is about waves, sounds, and light. So I think we are in a sort of like good position to decide when are we going to have the second exam. All right. But the bad thing was you didn't had a chance to look at the results of the first exam yet. But anyway, so we'll move forward. All right, so I have a proposal to make right here. So I think we can finish this chapter very easily today. It shouldn't take too long. And because as usual, we don't want to go through too much into the third module, which is going to be another series of lectures, which is they are all related and it's pretty much disconnected from what we are doing at this point. So I think maybe this is a good place to draw a line to say that, okay, this is it. So I'm thinking of, I would like to cancel Wednesday's class. Okay. However, I am going to have just like before. First, I mean, just like this is the reason is this because I'm thinking in my head you might want to take exam when, but just all right, I think I might have already like ahead of myself a little bit. Sorry. So when should we have the second exam? All right, that was the first question. All right, and I'm not sure you guys sort of like pretty like available at this point because I don't think it's gonna crashes with other exams. I guess I think you guys sort of like have a lot of free time at this point. Yes or no? So if you are okay, I propose that we should have the second exam uh, after heat death of the universe. Yeah. So I'm proposing that we should have exam on 14th. That's my proposal. It's on once again on Sunday. And it's going to be the same format. So this means you have plenty of time to do your exam. So I'm going to release the exam in the morning and you have until like 12 hours, just like before. So it's maybe 8 to 8 or 9 to 9. And then you just submit your work at night. Okay, sounds like a good plan. Is 14 a good day to you guys? Yes. All right. It seems like no objections at this point. Okay. All right. And the format, it seems to be open. So it seems to be no pressure on you guys too much to prepare like ahead of time. Okay. So no objections. So if that is the case, so I would like to repeat what we just did. And then I think I have received a couple of sort of like praise or something. It's kind of like you guys like it. So I would like to cancel Wednesday's class and I'm going to have like a Q&A session just like before on Saturday before the exam. Sounds like a good plan. Oh yeah, the practice, I forgot this one. I have already prepared a couple of them, so I'm gonna post it maybe just right after this lecture. All right, so I have quite, I mean, 2 or 3 sets of problems that I can pose after this lecture. Sorry, yeah. So you should have more practice questions. Yeah, definitely. So I'm gonna post that. I thought I could have done it. I haven't done a lot of stuff in the past week. So bad, so many things going on. And so you guys can try it and practice those questions. And then when you have questions, or if you want me to go through some of those problems, then we can do just like what we did last time on Saturday. Sounds like a good plan. And then on Sunday, then we have open sessions exam. Yep, sounds good. So no objections. So it seems okay. All right then. Okay, so if that is good for you guys, all right. So we'll do that. So we'll have the second exam on this coming Sunday. Okay, sounds good. All right, and I'm going to set the Q&A or review sessions just on right before that exam date. So it's going to be on Saturday in the morning. Sounds good. Like before, like 10 to 12. Yeah. Okay. All right. So it seems like everyone agree. Okay. All right. So that's set.
Okay.
All right. So let's get things done today, guys. So, but as you can see, the second module is pretty like light in comparison to the first, and I'm pretty sure it's going to be light in comparison to the last module. So this one is sort of like, you know, somewhere in between. You can relax a bit. The calculations are pretty much like, well, algebra, no calculus, like there's some geometry for you to have fun with, something like that. So this is okay. Okay, all right, good. So usually the second exam is the good one. I mean, the one that you feel comfortable uh, working through and then seems very confident for the results. All right, and I'll try to uh, have a chance to let you know the scores from the first exam before the second exam. Oh, that's so bad. All right, but I think I will do better on the second one. Okay. All right, guys. So let's finish this thing. All right, it's gonna be quite good because we have only one key topics that we want to attack today, and it's the image formation. All right, and you guys had already have everything sort of like enough to understand this. Not bad at all. Okay, so first thing first. All right, now we know that light reflects. Okay, so it depends on the medium that the light is trying to go through. For example, in this case, if you have a transparent medium, however, the shape of that medium is curved, as you can see here. And you guys know this is lens. Okay, so actually what is happening, it's happening on the surface right there. So every time you have light hitting a surface and then you try to change the medium, you have an incident angle, you have a refracted angle, but because you have the surface curve in that direction, so on the way out, all right, you get one first. Oh, this is so big. All right, I actually, okay, I think you can still see it. So from the first interface, you have some refraction already. But then on the way out, you have another interface, but then it's curved backward. So you have another refraction that bend the light even further down like this. Okay. And that's what happened when the light tries to go through a lens, is refract. That's all. However, it's curved in a way that all those rays eventually will meet at a single point on the back. And this is because this is an actual light ray that can cross each other. So we call this is a real intersections between those rays. And what you get right here is you can just copy what you have on the left side on the object, put it on the right side over here. And if you put a screen, then you can copy all the information of the object onto that screen. And we call that image. Okay, that's no big deal. But because this is the image that's formed by an actual rays crossing or the actual light actually traveling to that point, we call this real image. Sounds good? Okay, so that's the introduction. What does the real image means? So the real image is formed by the real light rays intersecting at the image points. Okay, and of course, now you can understand what does it mean by in focus. So that means if you sort of like move your screen a little bit toward the front, for example, like this, you can see that all those rays not hitting at a single point, and that is a blurred image. Okay, so you have to actually move your screen to a point of an actual intersection for you to have a clear, crisp image. That's what it is. Okay, now on the other hand, if you look at this one, this is a common scenario, is the light going through just a flat mirror. And this one we already discussed briefly, that if you have a source, when you have a source, mean it could be like from an object or whatever, and then all the light hit the mirror and reflects backward. And you can see that from the ray that is outgoing from the reflection is diverging. See that? Is diverging. So that means these rays, they're never going to cross each other. Impossible. Okay, so what happened here? So what happened here is there's no way that you can put a screen, because I mean the screen will be useless because light will never intersect themselves, and then you're not going to be able to focus anything onto a screen. So in this case, you never going to get a real image. You guys with me? However, though, if you place your eyes there, so you have an observer. Now your eyes has been trained I don't know how it's been trained or that's what it is. So when the light hits your eye, your brain will interpret that the object is directly in the front because the brain always understand that light travel in a straight line and everything. So if there is something sort of diverging and then it hits your eyes, then your brain will interpret that, hey, there is an object right at the origin of that light. So over here, once you place your eyes right there, then your eyes will interpret that, hey, this one is like there is a source sitting right here and it's generating the light and it's a diverging light that hits your eyes. So that means by the observer's eye, they can see that there's an object right here. So this is going to be a virtual position because light never travel behind the mirror. Cool. Okay.
Okay.
However, your eyes can perceive that there is some sort of like a source, a point source sitting at that point. So that's why we name this a virtual image, because the characteristic of the virtual image is actually copied from the point source. So it doesn't look exactly the same. So that's how you look at yourself in the mirror. You see yourself in the mirror, but you cannot touch it. You cannot, you cannot bring your hand and grab it. You cannot put like a paper, a film or anything just to capture your image behind the mirror. No, that's not possible. Okay, so the image from the mirror, that is a virtual image. So the virtual image is the image that is formed by extrapolating. So that is the mathematical words for it. So you extrapolate the lines, okay? And then they are virtually intersect at a virtual point. It's not, it's a real point, but it's a point behind the mirror, okay? All right, so it's not an actual crossing. All right, so I hope you understand the two types of images. So you have real image and you have virtual image. It clearly just goes directly by looking at where the lights go. Okay, cool. All right, there's a question comes in. Are we going to find local point? I mean, calculate. Yeah, we're going to calculate it. Of course, yes. Otherwise, then I can end this lecture right here, right now. Like, okay, guys, that's done. So you know how to classify the images and then, okay, bye-bye. Or then maybe you guys like it that way. Okay. All right, cool. So the plane mirror is the easiest one because everything rely on just a simple law of reflection. And then you know the incident angle equal to reflected angle, and then you're done, right? So that means if you look at just a flat mirror, okay, and then you just draw like a simple diagram, for example, you can pick a ray, let, for example, ray number 1 here, and you can draw another one, number 2, you can draw number 3 down here, number 4. You can see that by the law of reflection, the light that coming out is going to be diverging. Okay, let me highlight it in black over here. It's diverging. So what you do is you extrapolate that one toward the back. So they will look like they are emerging from the point IA behind the mirror. But because of the law of the reflection, the incident equal to the reflected angle. So that's why they call a mirror image of each other. So you just mirror image everything on the left to the right. So if you measure the distance of the object from the mirror and you call it P, you can name this an object distance. Okay, cool. And because everything is a mirror image, everything copy to the right with the reflection, of course. So you can measure the distance from the mirror to the point of virtual image, and that can name the image distance. Cool. All right. You can use P and I, or, I mean, it depends on what kind of things that you want to use. But anyway, one is for object distance, and the other one is going to be for the image distance. So for a simple conclusion is, for a flat mirror, the object distance is going to be equal to the image distance. Simple as that. So this is the reason why when you are sitting or standing in front of the mirror, you see yourself pretty much symmetric around the mirror at the center, okay? Because your distance to the mirror is going to be the same as the distance from the mirror to the image behind the mirror. Okay, however, things get more complicated when the mirror is curved. So there are some extra distance that we have to define, because look at this one. You have a curved mirror. And because this one, we assume that is a spherical curve. So let's assume that. So that means if you have a light that travel parallel to something that we can name it like a central axis. So it's the axis that cut in the middle of the mirror and split the mirror into two halves, the upper half and the bottom half. And if you have a light ray that actually travel parallel to this axis right here, let me name it the ray number 1. So when you have that hit the mirror, of course, every time you have to draw a normal line. You guys with me with that? Yeah, every time we do this normal line all the time on an interface. Then you have the incident angle equal to the deflected angle. Okay, and then if you do this in the bottom half of this one, it would do exactly the same. So these two rays is going to crisscross intersect at one point right there. And you call that a focal point. Okay, got that one? So far, so good. And actually, you can draw even more lines if you like. So that means you don't need to stop here, but it seems like you get a point that all you need to do is just you stick with just 2 lines or 2 rays. That's more than enough. But if you want to know more, I mean, you can draw another one and use the law of reflection again. It's going to come here. And you can, oops, sorry. And you can draw more. I mean, at any other distance, you can come, oops, sorry. If you want to, like, if you want to come out here, yeah, that's fine. With the law of reflection, it's going to get you there anyway, something like that. Okay, got that one? So that's how you pretty much use a ray diagram to figure out where the light should go. All right, and that is a focal point. So when you got the focal point, you can measure the distance from the focal point F to the center of the mirror. You can name this a focal length. Not bad, right? You got focal length. But then because of the law of the reflection though, from the look of it, if you extend your normal line that we just drew right there, and you just keep extending, because this is a spherical mirror. When you draw a line that is perpendicular to the surface of the circle, that line is going to cut through the center of the sphere. Make sense? Okay.
Okay.
So what you have over here is the distance from the point C is going to be the center of the sphere. So the distance from C to the center of the mirror is going to be the radius of the sphere. So this is the radius of curvature of this lens. Okay, cool. Okay, that's not bad. That's not bad. But then because of the law of reflection, you split this angle in half. Okay, so you think of it like you have this angle right here, the big one, and then you split it in half. So in terms of the distance, it's going to split the distance in half as well. So that means the focal length and the R is going to relate it through the factor of 2. So that means R is going to be twice the focal length. You guys with me?
Okay.
And that's pretty much the thing. Just knowing that the focal length is half of the curvature of the mirror. Cool. All right. So with that idea in mind, you can do further in the case of if the mirror just curve in the opposite directions. So in this case, you have the light that reflect and it's curved towards you. Yeah, towards you. Is it curve towards you or curve away? Yeah, curve towards you. All right. So when the curve is towards you in this case, then the light hit and it's going to bounce back, but it's bounce back in the diverging direction. So it's, as you can see, it's diverges. So what you're doing is just you extrapolate those lines. And they are virtually crossed at point F, but now point F is behind the mirror. You can still call this a focal point anyway. And the distance is still, you can call it a focal length just like before. And the center of curvature now is behind the mirror because it has to be at the center of the sphere. So that is still your radius. And the radius is still twice the focal length. That's no big deal. However, everything that you're having right here is virtual because everything is behind the mirror. You guys with me? Okay. In the left here, everything is real because light actually going to bounce back and cross themselves in the front of the mirror. So what I'm going to give you a conclusion at this point is, hey, anything that is going to happen and it's real, it's going to happen in the front of the mirror. You guys with me? light never go behind the mirror, of course, right? So anything that happens behind the mirror, anything it means, of course, the image, or you will see in the future that there might be a case that you might be able to place an object right there. But that's kind of weird at this point. Like, how can Ajahn place an object behind the mirror? All right, we'll sort of talk about that in a minute here. But what you have over here is, in terms of the mirror, light reflects. So when light reflects, you shouldn't get any light behind the mirror. Anything that shows up behind the mirror is going to be virtual.
Okay.
All right. That's the key. Virtual. Okay. All right. So that's a question comes in. What makes mirror reflective? Okay. So what you can do is, usually they put like a mercury layer, a mercury. So you put like a mercury on top, and then that's it. Just as you can just need like a thin layer of that one. Yeah. And that just make it nice and very reflective there. Yeah. Okay. Very cool. So what you have over here now is, how can you actually calculate the actual position of those images? That's what we need. All right. Overall, you might be able to do like a rough idea using those rays tracing. That's called ray tracing, because you just trace a ray. And then you do it multiple times. You take ray number 1, number 2, number 3, but actually you need only 2 rays. Once you get 2 rays, and then you know where those rays intersect, and that's it. You can pinpoint what should happen to the image. Does that make sense to you? Let's take a look at the first one, for example. So if you know how to trace rays using just law of reflection in this case, look at the ray number 1 there. Okay, but Ajahn, this is not bad, because you just have a light travel in the horizontal direction, hits the screen, it's going to bounce back and cross the focal length. That's good. That's ray number 1. This is fine. Or you might say, Ajahn, let's pick another one, whatever one that you want. What if I pick the ray that actually going through the focal point before hitting the mirror? Of course, by law of reflection, everything has to reflect back in the horizontal direction. There's only one law here. And that's it. If you name this line number 2 or ray number 2, then what you have here is number 1 and number 2 are intersecting at this point. You see that? And you are done. Done in the sense that because these 2 rays are so easy to draw, and you name this is your image location, is right here. And the distance that we talked about, if you measure the distance here to the center of the mirror, that's, you call it the image distance right there. Okay, and the position where the object stands with respect to the center of the mirror, you name that the object distance right there. Done. Okay. All right. So,
Okay.
well, you can keep doing this with other rays. But Ajahn, what if I have another ray, and this ray is so easy, Ajahn, because if you have, okay, let me write, just overlay on top of this one. If I have a ray that actually go through the center of the curvature, hitting this, you can guess what should happen. Of course, it's going to bounce back on itself, because you hit the surface of the mirror perpendicularly. So the reflection is going to go back on itself. And that's it. It's still crossing at the same point anyway. So you can draw as many rays as you like. But as I said, all you need is just 2. Once you draw 2 rays, you know where they are intersecting. Then you can point that point and then just say, hey, this is where the image is going to happen. Okay, cool. All right.
Okay.
And in this scenario over here, because you see this, the image happens in the front. Right there. Woohoo. Woohoo. Same thing. I mean, these 2 diagrams are exactly the same. So what you get is a real image. And it's going to happen in the front of the mirror. So that means I can place my hands there, and the arrow will show up on my hands. Does that make sense? That's what it means by the real image, something like that. Okay, this is pretty cool. All right. So whatever you get over here is, all right, I want you to think about it a little bit. What actually this kind of mirror shows up in your everyday's life. This is the one that you probably have seen. Is I think I don't know what you call it. It's like a cosmetic, like beauty products. You have like a big giant. It's not giant. It's like a big mirror that you can sort of like use to zoom into your face and do the makeup and all this stuff. This is what it is. All right, and we call this the mirror that curve away from you a little bit is the concave mirror. So this is what it is, concave mirror. All right, but I mean I think it's more easily to understand. Just say it's converging. I think this is a converging mirror. All right, so this is what you can see in, I don't know, supermarkets or whatever. Yeah, you can get that one. All right. On the other hand, if you have the mirror that curve towards you, we call it a convex mirror. If it's too hard or confusing between concave and convex, just do the diverging mirror, because the ray that hits this kind of mirror will diverge out. Okay. So in this case, once again, you can trace some rays and then you can see that they intersect behind the mirror. Everything that happens behind the mirror is going to be virtual. So this is a virtual image behind the mirror. And you can see that the size is kind of smaller in this case. All right, but it's still upright. So it means it still look not inverted and everything. So what you have over here is, this is a scenario that you probably have seen before. It's just the diverging mirror at the corner of the street or the road, that then you just want to know what is going on the other side of the road and all this stuff. All right, it's a convex mirror. Concave and convex. So let's just use diverging mirror. This is good. All right. So what you have over here is, all right, I'm still put a question mark here because this diagram is not representing this scenario. You got that one? Right? Because the diagram over here is showing the real image. But what you see over here is a virtual image. So if you just want to have fun with this, I mean, you should be able to draw a diagram that represent what is in this photo right here. Okay, this is supposed to be a virtual image because this is an object. The image is behind the mirror. So this is going to be a virtual image. Okay. All right. So that's what's supposed to happen. All right. But anyway, so the reason that I say I don't want to deal with the mirror too much, because in reality, the device that use mirrors like this is way less than the one that use lens that you saw in the first slides over there, that we use the transparent medium to reflect lights. So the mirror reflects light, but then the transparent material refracts light. So we're going to move forward, and then we're going to spend a lot more time with lens. All right. But the mirror, the concept stays the same. So this is the reason why I want to introduce to you the mirror first. Okay.
Okay.
All right. Now, let's come back here a little bit, because now you have a scenario over here that you can see that this is inverted image. So it means that the image that you get is upside down relative to the object. Second is it's smaller. See, it's not as tall as the original object. So there must be some quality of the, it's not quality like that, but it's a characteristic of the image that you're going to get out of the mirrors or lens system. So that's why we talk about the magnification. All right. But the simple concept of the magnification is just take the image size divided by the object size, and then you're done. So that's okay. That's easy. However, we would like to have a more concrete way that we can actually determine, hey, the final image is actually inverted or upright and everything. So I prefer this relationship better. So let's take this one. So if you take an extra negative sign to this expression of the magnification equation, and then you lift that absolute sign out, so just forget about the absolute sign. So this is going to be a real, not a real M, is an M that can have positive or negative value. It turns out you can calculate the image size over object size by doing the, now you might get confused a little bit here because we use a different notation, but they are meaning the same thing. This is the image distance. So this is the I that you saw in the previous slides. So this is the object distance. Okay, so that means the ratio between the image distance and the object distance will give you the magnification automatically. That's kind of cool.
Okay.
However, we want you to just forget about the absolute sign and just keep the negative sign there first, because at the end, if the M is positive, then you can interpret right away that the final image is upright. And if the M is it is negative, so it means the final image is inverted. So it's kind of like good that this M will give you two informations in one step. So it will give you the value of the M, the magnification. If it's going to be getting bigger, if M is larger than 1, or is it going to get smaller when M is less than 1? And the sign of the M will give you the upright or inverted type of the image. So is that a cool?
Okay.
You see in the example right now, it's just like me talking, just like, okay, what is going on here? But you'll see that once we do a couple of examples, yeah, everything will be easy. All right. And it's going to be like super straightforward to do. Okay. All right. So got that one. Then what is the equation that you can use to determine the image distance? And that's it, guys. We call this mirror equation. I don't know, have you seen this? But this one probably popping up in science or whatever in middle schools or in high school science or all this stuff from time to time. So it turns out is a reciprocal relationship. So it's 1 over. So you can see that it's 1 over P, 1 over object distance, plus 1 over Q, the image distance, is going to be equal to 1 over F, the local focal length. And that's it. So I can name this equation number 1 because this is the main equation that we're going to use. And then you can name this equation number 2. This is sort of accompany the equation number 1. So you can pretty much determine what type of the image that you're going to get at the end. Okay, sounds very good. All right, so that's all you need. The only thing left for you is just to make sure that you know how to use these values, because it could be positive, it could be negative. All right. And the concept that I'm going to give to you is very simple. The object is pretty easy because it's clear. Most of the time, it's going to be positive because you place the object in the front of the device. It could be like a mirror, it could be lens, whatever. But I mean, the object is object. So you can take that one as a positive side. So the object is positive when it's in the front. But when the object is going to be in the back. All right. So that case, you're probably going to talk about virtual object. That's kind of weird, but don't worry about it. Think about it if you have multiple mirrors. So when you have multiple mirrors, the technique is like you do the calculation 1 mirror at a time. But there is a possibility that the image from the first mirror might give you, of course, the image from the first mirror will be taken to be the object for the second, right? So for you to do the second steps. And that is when there is a possibility that the image from the first mirror shows up behind the second mirror. So your object distance turns negative in that case. Okay, sounds good?
Okay.
However, if you have only single mirrors, of course, objects stay positive at all times. Okay, that's not bad. Okay, so that's easy conclusion there. Okay, now the most confusing part will be the Q, the image distance. That's the part that is going to get more confusing. But if we stick with what we are knowing, once again, image is going to be real when it's in the front. Okay?
Okay.
And it's not going to be real when it's behind. And that is my only conclusion, guys. So for the image, things will be positive when it's in the front. And it's going to turn negative when it's in the back. That's it. That's how simple it is. So that's why the conclusion that they make in the table over here. I don't know you like this table or not, but if you like it, that's okay. So it's positive when the image is in the front for the mirror and it's in the back, then you're going to get a virtual image. But key concept is positive where light goes.
Okay.
The light supposed to reflect. So this means light supposed to shows up in front of the mirror be after the reflection. So positive is in the front of the mirror. That's it. That's the only sort of like rule of thumb that you can pretty much grab and go and then just be happy with. All right, I'll show you with some of the examples in the future. It seems going to be a lot easier to understand this. All right, almost done, guys. If you understand this, sort of like lens is like in, like a super duper small stuff, like after effect of this one. Okay, you have a concave spherical mirror. Let's go through this one together. All right, slowly. You have a concave spherical mirror, has a radius of curvature of 20 centimeters. So that's good. So that's R is given. All right. So now find the location of the image for object distance of 40, 20, 10, and then on and on. For each case, state whether the image is real, virtual, upright, inverted, and what is the magnification. So it means it asks you to do everything pretty much. All right. Okay, let's go for it, guys. You have only two equations to deal with this. 1 over P plus 1 over Q equal to 1 over F. The reason that, well, I tried, well, it wasn't intention that I want to change or switch the notation for the image location, object location, or anything. But if you look at the textbooks, I don't know why for this particular topics over here, there's so many notation that they use. They can use S and S prime. Some use U and V. Some use like what they just use in the earlier part, I and P. I don't know. And some use like object is O, image is I. I don't know. It's crazy. And what we're using here is P and Q. So pick your equations. I don't know. It's just, I think maybe it's just the concept is so simple enough that people don't really care much about what you want to use to call object location or object distance and image distance. I think it's just, they're going to be both of these terms adding together. So that's it. Just pick any two. Okay. All right. But we stick with P and Q then. Okay. So what you have over here is this is the equation number one that you're going to use all the time. And you're going to have the magnification that I asked you to just stick with the negative sign thing, no absolute. So you won't have to confuse whatsoever at the end. So I'll show you what it means by no confusion toward the end. Let's start with part A, guys. The object distance is 40 centimeter. So that means P is 40. And because it's a single mirror, it's always positive. So I put positive sign there. Okay. F, now the focal length. This one is a concave mirror. So if I draw a diagram on the right, concave is this one right here. Okay, the focal point is in the front. So that's a capital F right there. So the focal length is also in the front. So I said anything that is in the front that is positive for this mirror. So when not this mirror, but it means for the mirror in general. So F is going to be positive 20 centimeter. So that's why if you look back in the table here, it's going to be positive when the the mirror is concave. So you got that one? Okay. So that's why I said just stick with the principle. I know you call this principle not, but stick with the where the light go. If light's supposed to reflect in the mirror, so whatever for the image that shows up in the front, that's gonna be real. So focal point is in the front is supposed to be real. So real is positive. All right. So what you want to figure out is what is the image location. So you just put it in there. 1 over Q equal to 1 over F minus 1 over P. It just flip things toward the right side. 1 over F is 20. 1 over P is 40. As you can see, I don't need to do unit conversions as long as I keep same units in all terms. All right. So this means I'm working under centimeter units. So my final result will be in centimeter. So that's good. No big deal. Okay. All right. So what you have over here is, whoa, what is that? So it's 2 over 40. So that's fine. So what I get is 1 over 40. Am I right? Good. So what you have over here at the end means that Q is 40 centimeter. Nice. Okay. As you can see, the final answer is still positive. So what does it mean? It means you place in here, R is 20 centimeter. Okay. My bad, guys. I forgot to divide it by 2. My bad. Sorry. This is like a big bad. No. Divided by 2, guys. Oh, sorry. So here, let me write it down right now. So F is going to be 10 centimeter. My bad. That's why the numbers look so weird. All right, so it's going to be 10 right here, but it's still positive. Okay, that's better. There you go. So this is going to be 10. So this is going to be all wrong here. There you go. All right, so it's going to be 10 right there. Oh, that's better. All right, so what you have over here is it's going to be 3 over 40. So that means Q is going to be 40 over 3. And let's say it's about what, 1.13.3, somewhere like that. Okay. And it's still positive. So I can just park the sign right there just to make sure it's clear. So what you have at the end is this. So you have an object, okay, located at 40 centimeters. So it's way out here. So let me try to here, maybe here, that object right there. Okay, in front of the mirror. But then what you get at the end is positive 13.3. So it's somewhere here because this is 10, half of the radius, you get the focal length. So this one is 13. So it's a little bit, to your left relative to the focal points. So that is your location for the image. Positive means it still stays in the front of the mirror. Cool?
Okay.
All right, now let's do the type of the image. So I use the second equation, m equal to negative q over p. Now I plug in the q, which we just got to be 40 over 3. And I plug in the p, which is 40 centimeter. There you go. Okay. And that 40 cancel, I get negative 1/3. So 1/3 means the magnification is 1/3. So it's going to be reduction in size. So it's going to be 1/3 tall relative to the height of the objects. Okay. And then it's negatives mean it's upside down. So in conclusion, your image will look like this. Smaller. 3 times smaller. So if this is like 1 meter tall, this is going to be 1/3 of the meter tall, and is upside down and located at 13.3 centimeter in front of the mirror.
Okay.
And this scenario looks exactly just like what we just did over here. See that? Okay, so you have focal point, center of curvature. You place an object behind that center of curvature. You get an inverted reduction in size image in front of the mirror. So this is a real image. All right, so that's it. So in conclusion, you get a real inverted image. Okay, and 1/3 the size of the object. There you go. Done. Cool?
Okay.
Only me. Okay. All right. Try again. All right. Let's do one more and then we'll take a break. Sounds good. I think this is a sort of easygoing portion of the material. Part B. Right now, it's sitting at 20 centimeters. So it's mean for part B, P is positive 20 centimeter. Focal point stays the same at positive 10 centimeter. So what is the Q? You say 1 over Q equal to 1 over F minus 1 over P. So it's going to be 1 over 10 minus 1 over 20 now. And that will be 1 over 20. And that means the Q is 20 centimeter. There you go. All right. And that's not bad. The reason is not bad because this is to be expected. You place your objects right at the radius of curvature right there. You place your object right here at the C, the center of curvature. by law of the reflection, everything will just reflect back to itself. So that's why your final answer stays at exactly the same distance, because it's a reflection back to itself. Okay. However, stick with the plan. The M is negative Q over P. Q is just plus 20. P is plus 20. So it's negative 1. So what does it mean? Because of the reflection, the size shouldn't change. So you still get no magnification or reduction. It's just the same size. So this is why magnitude of M is 1. However, you have a negative sign. That's because it's going to be inverted. Same size. Does that make sense to you? Yeah, it has to be inverted because it's reflection.
Okay.
So image will go upside down. Cool. All right. And of course, part C, let me use a different ink a little bit here. All right. So C, now you place your object right at the focal point. Now F is equal to 10. And P is also equal to 10. So now I can jump right into this expression over here. 1 over Q equal to 1 over F minus 1 over P. But F and P are exactly the same at 10. Whoa, you get 0. So if you flip it over, Q is going to be infinity. So what does it mean? Of course, you place an object right at the F. Okay, the light will pretty much reflect and go out horizontally. Remember this one, right? The diagram, the ray diagram that we did before. So this is why from this equation, it will give you the infinite, sort of like you going out with a parallel ray of light or something like that. So they never going to cross themselves. So that you don't get any focus at any distance. So that's why they say Q is infinity, means you get just a parallel light on the way out. Okay, but that's, I mean, in the reality, you're not going to be able to place an object right at the spot. So, but of course, if you just take a light at the spot, you're just going to get like a beam of the light coming out straight. So that makes sense in reality. Yeah, and that's what they use when they use like a satellite dish. Yeah, so think backward. So when the signal coming from the space hit that satellite dish, they try to focus everything into a focal point, and they have like a receiver right here to receive the information from the magnetic waves from the satellites. So, all right, that's the focal point from a parallel beam. So that makes sense. So this is just an inverse of that. You place a source at the focal point, you get a beam out. Okay, sounds good.
Okay.
All right, so that's actually the first half of this lecture about finding the image location from mirrors. But then after the break, you will see, I will show you one more time with the lens system. But things will go very, very easy now because you understand how to deal with the mirror. The lens will be exactly the same after the break, guys. All right, see you in 10, yeah? What to do is have fun with my sound effects here. I'm alive. Okay, guys, almost done. I promise you, this is going to be super fast if you take the idea that we already established from the mirror. The concept is very easy. All right, guys, take a look at this. Now, instead of having something that is reflective, you sound quiet. Oh, what did I do? I haven't done anything. I think it's okay now. Maybe there was the mic was a little bit too far away. Okay, so what you have right now is instead of having something is reflective, now you have something that is transparent. So the light, instead of get reflections, it get refraction after the interface. Does that make sense? So this is lens. And they say it's thin, all right, because we assume that we don't want to take into account the thickness of the lens at this point. It's just too complicated. So assume that the lens is thin enough. When you say thin, means you take this to be approaching 0 thickness. So it's super, super thin. It's in theory, you can tell. All right, so with that idea is you still have 2 types of lens. One is converging, one is diverging, just like in the mirrors. However, when you do the converging, is converging toward the back side of the lens, and that's it.
Okay.
So you can guess บอกอาจารย์ this is going to be positive focal length. You guys with me? Because for the lens, light supposed to go through. So anything that actually going to happen in a real scenario is going to happen behind the lens. You guys with me? So anything that is related to the image from the lens, if it's going to be real, that has to be behind the lens. So anything that is behind the lens, we take it to be positive side. That's positive. And nothing should shows up in the front anymore. So anything that shows up in the front, you can guarantee that is going to be virtual. So this is the virtual part. And definitely this is a negative sign. Okay, sounds good. All right. Yeah. So there's a comment from your colleagues here saying that I remember burning ants by focusing sunlight. Yeah, that's, yeah, maybe I didn't burn ants, but I think I just burned a paper. But I think everyone tried that. All right, that is a focusing lens. That's what you probably have experienced before. But anyway, just to confirm, because this one is so close to your life a little bit in the sense that I'm wearing glasses and my glasses made out of these two lenses. Okay, so in my case, well, it's this type because I have a nearsighted. So what you have is I have a diverging lens. However, in the reality, for those of you that are wearing glasses, you can see that the curvature of two surfaces of your lens going in the same direction. So this is what it is. It's this type right here. That's your glasses made of in this case. So the key of the diverging lens is as long as the center is thinner than the rim, doesn't matter what shape of this one is going to be, you're going to call them diverging lens no matter what. Because toward the end, after the light coming out of this lens, the light will have a diverging direction. On the other hand, as long as you have the center of the lens thicker than the thickness toward the rim, you call them converging lens no matter what. Okay. All right. So that's what it is. Now, how can we calculate the positions type of the image? Look at this one. Well, Ajahn, this looks familiar. It's a ray tracing. However, instead of tracing backward because there's no reflection anymore, you just trace the ray forward going through the lens. But the concept stays the same. You just need two rays that you know where the light will travel, and then you just find that intersection. For example, look at the ray number one on the top. It hits the lens, and this is a converging lens. It's a convex lens. Then parallel light will bend the light and hit the focal point, just like the same as before. But in the mirror, you do this reflection to the focal point in the front. But in this case, you're going toward the back because it's transparent. All right, but the concept stays the same. Does that make sense? All right, another point that you know what to do is if you have a light going through the focal point, the reflection, I mean, the equivalent focal point in the front, hitting the lens, then you know that it's going to come out straight like this. It's just an inverse scenario from the ray number one. Okay, that's cool, John. And there is another ray that you can actually put on top over here is the one in the middle. So if you have a ray that actually hit the lens at the center, so in this case, it's just a flat area of the lens. So think in terms of the mirror. If this were to be a mirror, all you do is just do the reflection here, right? But for us, I mean, for the lens, it just goes straight out. Nothing happens because at that portion of the lens, the surface of the lens is just flat. So when it's flat, there's no refraction. I mean, the reflection doesn't really do any divergent, convergent. It just shift a little bit. But because we said that lens is so thin, so this means you can think of this like there's no thickness of these two layers or two interfaces. So light just doesn't, light don't feel anything at all. It's just penetrating through. So, I mean, you can draw other lines, whatever you like, but all we need is just two. So that's it. Your intersecting point shows up right here. And if you measure the distance from the lens to that location, that is your Q image location. And because this happens behind the lens, so this is going to be positive Q.
Okay.
Got that one? All right. And that's pretty much it. That's it. I don't know what else to talk about. For example, I know what else to talk about. For example, this one. All right, try this. You have a converging lens just like before, but now you move your object so close to the lens. All right, you draw some known lines. Let's get to the easy one, Bojan. I know this one is easy. The one that go through the center of the lens doesn't do anything. All right, that's lens. That's ray number 2 there. Another one that you know how to draw is the one that goes parallel to the principal axis will bend toward the focal point. All right, Bojan, this one I know how to do. Oops, sorry. There you go. All right. Actually, you can be done with this. You can see that ray number 1 and ray number 2 already diverging behind the lens. So all you need to do is just extrapolate. Tick, 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 tick. You extrapolate to find where they're supposed to cross. And they are virtually crossed in front of the lens. This is not where the light's supposed to be. Light's supposed to already penetrate through the lens and go out on the back side. So this is going to be virtual. With me, guys? That's it. And this distance over here that you're going to be able to calculate is going to give you the negative value of it because it shows up in the front, the same side as the object. Done. So that's the scenario. And what you can guess what this is the magnifying glass, of course, right? When you have like this could be like a letter in a book, and then you put a magnifying glass close by, then your eyes can see that this letter just get enlarged, magnified. But it's virtual image. You cannot touch it. You just see that letters are bigger, but you cannot do anything with it because they are virtual images. Okay, sounds good? All right, and then you can keep doing this, and now you can pretty much get to a conclusion about Ajahn. So the converging lens, the focal point is supposed to be positive focal point because your focal point shows up behind the lens. That's where the positive territory for the lens is supposed to be. But then if you have a converging lens, your focal point is in the front, and this is going to be negative territory for the image from this type, from the lens. So this is going to give you negative focal length. Done, guys.
Okay.
Cool. Apart from this, but I can still use the same combinations because same logic, same thing, everything is the same, except you just change from reflection to refraction. So everything just flip backward, that's all. So you can still use these two equations just like before. And you can now name this thin lens equation. But they are exactly the same as the mirror equations. And the magnification equation stays the same with the negative sign in the formula for you to be able to do the direct interpretation of the M after calculation. Sounds good? All right, let's give it a shot, shall we? All right, instead of going through this table, you can go back and take a look whenever you like, but let's do like a natural way. Attack this problem just like you don't know how to do it, but you know how to do it. All right, an object is located 20 centimeter to the left of a diverging lens. Now they say diverging lens, so that's good. Having a focal length of 32 centimeters. So you have to know in your heart that this is going to be negative 32. You guys with me? Because it's a diverging lens. The focal point is in the front, and that is the negative territory for the image. Okay, now determine the location, the magnification of the image. Actually, I can throw in the type of the image and the orientation of the image too, if you want. Okay, so we'll do them all. So let's start with, once again, 1 over P plus 1 over Q equal to 1 over F. What you want is you want the location is the Q. So it's 1 over Q is 1 over F minus 1 over P. Okay. And your focal point, focal length is negative 32. You already got that information. And now you subtract out with the here object is located, and this is a single lens system again. Wherever the object is located, the distance is going to be positive automatically. There you go. Cool. All right. So with this, just work things out a little bit. So I'm just find a common denominator. What shall I do is a negative sign. So, okay. So you can work this out whenever you like, whatever you, I'm going to make mistakes right here. 32 times 20. So it's going to be what? 52 on top. Okay. It's not bad. All right. With a negative sign. Okay. All right. And that's it. Your Q, I'm just going to leave it there because it might be useful later in the future. 32 times 20 over 52. All right. Cool. So as you can see, your final answer is negative. So what does it mean? It means you're going to get an image in front of the lens. So if I draw a diagram for you, so this is going to be diverging lens over here. Okay, the focal length is 32. That is 32 centimeter. Let me put it behind here as well. All right. And then you put an object 20 centimeters. So it's sort of like somewhere here. That's your object right there. Okay. But then what you get at the end is this value, which is, I mean, I can approximate. How much is this? It's about like, let's say 120 or so. Is that right? No, that's too big. 1.2. Sorry. Is that right? 12? Yeah, 12? Yeah, 12 centimeter. Yeah. Is it good? It's my bad. I mean, if I just punch the calculator, it will be done. All right. So let's say it's about 12 centimeter. So that's mean your final image will show up somewhere here. Negative 12. So that's right there. With me? Okay, the object is at 20. This is 20. So your image will somewhere here. It's closer. It's only 12, but it's in the front because it's negative sign. Okay, now let's combine this with the magnification equation, minus Q over P. So it's going to be negative Q, which is, okay, let me pull the whole numbers there. 32 times 20 over 52 divided by the object location, object distance, which is 20. So these two cancel. So what you get at the end is negative 32 over 52 there. So that means your final object will be a little bit smaller, about 3/5 or so. Yeah, so it's about 60% tall. But then negative sign means it's going to be inverted. So it's going to go upside down. So this is what is going to happen there. Cool. All right. So this is done.
Okay.
So that means what I can tell at the end is I can give you every information. So it's going to be virtual image because the final Q is negative. Virtual image. Okay. Inverted. Reduced in size. I know it's going to be 32 over 52 times the original. Something like that. All right. Virtual image, inverted, reduced in size, located at 12 centimeter in front of the lens. Done. Woohoo. All right.
Okay.
So I'm just showing you that that's all I'm doing is just taking equation number 1, mirror or lens equation, and equation number 2, magnification equation. And then I can pretty much solve everything about image formation from lenses or mirror system right there. Okay, very good. All right, so I hope you see what is about to happen when you have, this is going to be our last exercise and I think be done with. But not talking about this one is kind of like illegal. because it's an application of this and it's a simple application, but I hope you will see the connections, and then whatever that's rely on this kind of technique is going to pretty much be so clear to you that you can multiply this in as many as you like. And it's the combinations of lenses. So what you have over here is, if you have more than one lens, like this one, you have two lenses next to each other, and they just want to know, hey guys, what is the final image from this lens system? How would you do it? Well, okay, this is not bad. The way to do it is you just do it in step. So you start from each lens one at a time. Okay, take a look at this. So for example, you have an object. This is a weird one. They have a pencil with the tip down. That's kind of weird. All right, but anyway, it's not weird, but just make sure that you do the tip down. I think it seems like I thought at first it's gonna be tip up, the tip of the pencil, but the tip of the pencil is down on the table somehow. Okay, so you start from the lens number one. You do just like you did, 1 over P plus 1 over Q equal to 1 over F. You're going to be able to determine the image location from the first lens. So take a look at this. It turns out, let's say that from this diagram, the location from the first lens give you the image right here. I highlighted red over there. Okay. Now you take this image from the first lens to be your object for the second lens. Got that one?
Okay.
That is not too bad at all. Now for that means all you need to do is just determine the distance one more time. And as you can see now, this is a chance for you to hit the negative object distance, or they call it a visual object. It depends on the location of this image right here. If this image, which is going to be the object, is still sitting in the front of the second lens, you can still get a positive P, the positive object location. But think in the scenario that if this image shows up right here, for example, now your P will show up behind the second lens. This will give you the negative P now. Okay, all right. So that's what negative object distance might occur. Usually it will occur in a multiple lens system. Okay, so in this case, once you understand how to deal with this, so you just go back and then take a look at the setting for the lens number two, and then you're pretty much almost done. Take that new object location and then just recalculate the image one more time. That will be, in this case, it shows up right here. So that will be your final image location. So let me put subscript 2 so you won't get confused. So this is the second step. There you go. So this is going to be P sub 2. That's your object location for the second lens. And you're going to use the same equation again to determine the image from the second lens. And that will be your final image. Sounds good?
Okay.
That's not too bad. All right. But then the good thing is, if the lens number one already give you some magnification, let me call it M sub 1. And lens number 2 will do another magnification, let's call M sub 2. You can guess the final magnification of the image will be just the multiplication over multiplication, right? It's just multiply and multiply again. So the total magnification is just going to be the product between those multiplications of each lens. Done. All right, guys, you want to give it a shot and see how it goes? All right, just like a finale of the second module right here. So this is what it is. All right, so you have two lenses separated by, it's supposed to be lenses, yeah? Two lenses separated by a distance of 40 centimeter and are used in combination, just like this is the same scenario that we just saw. The focal length F1 is given, F2 is given, an object 4 centimeter high is placed 15 centimeter in front of the first. Now, what is the intermediate and final image distances? Okay, they want everything pretty much. So, all right, so we're gonna do step by step. Let's start from the lens number 1, guys. I think you guys can go very quickly on this one now. So let me mark like lens number 1 there. 1 over Q sub 1, that's what I wanna figure out. It's gonna be 1 over F1 minus 1 over P1. You guys with me? I just move 1 over P to the right-hand side right away. So now, because it's a converging lens, so this is still a positive focal length for the lens. It's a converging lens. So it's going to be 1 over my plus 10. I'm just using the centimeter unit. Don't need to convert anything. Minus 1 over, now you place an object 15 centimeter in front of the first lens. So that will be positive 15 on that. Cool. So far so good. All right, I can work on this one. The number is not too bad, I hope. So it's gonna be what? That's gonna be 3 minus 2 is 1 over 30. There you go. All right, I think this is good. Am I doing it right? Yeah, 3 over 30 and 2 over 30. Okay, all right. So that's 1 over 30. So that's good. So that give me Q. Let me, oh, maybe it's just not good. Just writing too far. 1 over 30. And that means Q sub 1 is 30 centimeter. Woohoo! Good. So that's what you get. See over here? Okay, here we go. I'm back. Is that right? It's built in the software already. All right, good. Thank you. Internet was down, I think. It's just everything just completely shut. I mean, it's not shut down, but it's just connection is down. I think it's back. Okay, almost done. All right, let's get back to this. So what we have next is, where were we? So we get Q1, so that's mean 30 centimeter. So object is at 15 centimeter. So this was right here. So let me sort of highlight it on top here. It's 15. Okay. And then you get the location for the image is 30, but it's positive. So that means it's going to be behind the first lens, 30 centimeter. That's good. That's nice. Now we can move on to the second step. Because they said that the distance between these two lenses are 40 centimeters. This is 40 centimeter. So that means your distance from the first image, which is going to be your object for the second lens, is going to be 10 right here. Cool. So let's do that. Second step, your P2 is going to be 10 centimeter. Cool. All right. And then your F, your focal length for the second lens, is already given to be positive again because it's also a converging lens. It's positive 12. So let's go for it then. Whoa. Go for it then. So what you have here is 1 over P. Okay, let me do 1 over Q2 is going to be 1 over F2 minus 1 over P2. Cool. Already. All right. Let's plug in the number 1 over 12 minus 1 over 10. Nice. All right. And this one, all right, let's do a little bit of calculation here. Is 1 over 20 is like 10 and it's minus 12 on and on. So it's going to get negative number at the end. And that is negative 1 over 60. Oh, my handwriting is bad. Okay. 1 over negative 1 over 60. Sweet. So from here, then your Q2 is negative 60 centimeter. What does it mean, guys? Negative means it's shoot back to the front. So as you can see, this is your object on the second step, 10 centimeter away from the lens number 2. But then your image is in the front as well, 60 centimeter. So there you go. It's in the front, 60 centimeter. You guys with me here? Cool. All right. Now, At least now you know the final location of the object and it's right here. Now let's turn our attention to the magnification, shall we? All right, let's go back to the step number 1. You're going to have M1. Step number 2, you're going to have M2. Okay, but then M1 and M2, you do them separately if you like. M1 is just negative Q1 over P1. Stick with the plan, stick with the relationship that we had. So we have negative Q1 is plus 30 centimeter. P1 is just plus 10. So that means it's the negative 3 from the first lens. So the first lens, what it did was sort of like multiplied 3 times. But negative means the image of the first lens is going to be inverted, which is perfect. It already shows up in the diagram right here. See that? So what you have over here is the first lens give you triple the size and it's inverted. Cool, keep it there. But anyway, we can do M2 right here. The second lens, stick with the expression over here. It's going to be minus Q2 over Q1. Go ahead. Q2 woohoo, is negative. So that means it's going to be negative 60 up here, divided by the distance, which is only 10. It's right there. P1 is 15. Oh, yeah. Sorry. My bad. I circled the wrong one. Thank you very much. I want to check that you guys still with me or not. Sorry, my bad. Okay, here. Okay, sorry. 15. And that will be 2. Okay. Thank you so much, you guys. There you go. All right, thank you. Okay. All right, so come back to our M2 over here. It's going to be positive 6. So what does a positive 6 means? Just the second lens alone, you starting from here. See that the object is right here. You get at the end 6 times. How many times? 6 times. 6 times. 6 times bigger. Woo! Right there. But it's still upright. When we say upright, mean it's still the same orientation as the object because your M at the end is positive 6. Okay, you got what it means now to interpret the final results, yeah? But then you can combine this into your total magnification because now you already calculated M1 and M2. So what I'm doing is M1 is negative 2. M2 is positive 6. You get final total magnification of negative 12. Isn't that cool?
Okay.
What's cool? Here, you started out with the You started out with the object right here. But the final answer is negative 12. So it means at the end, the objects will be 12 times as big. And it's upside down because it's a negative 12.
Okay.
So you know how to pretty much apply mirror or lens equation plus magnification equation. And once you get the results, you know how to interpret them very easily. So you don't need to worry about this is going to be real. I don't know. It seems like stick with the relationships. You only need these 2 equations and then you're good to go pretty much. Very good. All right. And you kind of like know what this is. Yeah, this is, you could probably say, Ajahn, this is microscope. Exactly right. So what the microscope is doing is just you have the objective lens, right? And that's the lens that near the objects. And then you have an eyepiece, the one that close to your eyes. So if you adjust the focal length of the objective lens and your eyepiece, then you can do multiplication of maybe 60x, 100x. That's doable. Just only use the 2 lenses system. All right, but and then of course you can go more. You can go like crazy, 3, 5, 10 lens system, if you like the one that you saw in your smartphone, for example. It's just when you have like a internal structure of the phone, and then they have to sort of like split them out and show you what's in there. you can see that that's like multiple lenses system in there. All right. But of course, not only just the focal length that they want to adjust, they want to adjust the quality of the image as well. So what we're learning over here is we assume spherical lenses, but in reality, the sphere is not good as a focusing structure or geometry. The better geometry, or it's not better, but actually it has to be, is the parabolic curve. So you need a parabolic surface for you to be able to do like a real sort of like a fine focal points and all this stuff. So it's not as spherical, but mathematics is easier for the sphere. Okay, and the satellite dish that you saw, it's supposed to be like parabolic curve, not supposed to be a spherical curve. Yeah, that's what it is. All right, but anyway, there are some like other artifacts that you get from just a simple lenses, like color aberration. The color will not be perfect, and you get like maybe spherical blur. You have so many things going on with the lenses system. So that's the reason why the lens that you use in your maybe SLR camera and all the stuff is going to be so expensive because they have to manufacture them to eliminate all those artifacts. Yeah, they want to sort of get rid of all this, all that, all those until you get like a super sharp image. Okay, that's what it is. But what we learned so far is just so simple. It's like way too simple than what is actually going to be happening in the real consumer products. All right, but anyway, you get the idea of how to be able to calculate the object image distance from object distance and known focal length. Okay, sounds good, guys. Okay, not too hard, but I think this is going to be the representative of the question that will show up in the exam. This is going to be the upper limit. It's not going to be anything harder than this. Okay, and it's, I think maybe most of them will be just simply using these two equations and then you just combine them into a final image and then you're done. Okay, sounds good. All right, guys, and that is it for
Okay.
okay, all right. And so we agreed to have the second exam on this coming Sunday. All right. And I'm going to set up a Q&A sessions or review session or whatever session you want to call it on Saturday morning. All right. For those of you that can attend, feel free to join. If not, that is okay. I will do the recording and then you can catch up later if you like. Okay. Sounds good, guys. All right. So exam is on 14th. All right. And I'll see you guys on 13th for Q&A. I'll see you guys soon. All right. Take care, everyone. Stay safe. Bye-bye.